What if I told you that one of the most beautiful identities in algebra was discovered by someone who had to pretend to be a man just to study mathematics? Today, we're going to explore Sophie Germain's identity, an algebraic expression that looks completely impossible to factor until you see it through the lens of geometry. And by the end of this video, you'll understand not just the identity itself, but 3 different ways to prove it and why it matters in number theory. But first, let's talk about the remarkable woman behind this identity. Sophie Germain was born in Paris in 1776, the same year as the American Declaration of Independence. At 13, she discovered mathematics while hiding in her father's library during the chaos of the French Revolution. She read about Archimedes, who was so absorbed in a mathematical problem that he didn't notice Roman soldiers breaking into his city. According to legend, his last words were, "Do not disturb my circles." Sophie thought, if mathematics could captivate someone that completely, it must be worth studying. Her parents were horrified. Mathematics was not considered appropriate for women in 18th century France. They confiscated her candles, they took away her clothes and her fire, leaving her to freeze in her room at night. But Sophie wrapped herself in quilts and studied by the light of smuggled candles. Nothing could stop her. To correspond with mathematicians, she invented a male alter ego, Monsieur Antoine Auguste Le Blanc. Under this name, she exchanged letters with Lagrange and later with Gauss himself. When Gauss finally discovered that his brilliant correspondent was actually a woman, he wrote one of the most beautiful tributes in the history of mathematics. Now let's look at the identity that bears her name. Here it is, a to the 4th power plus 4b to the 4th. At first glance, this expression seems completely unfactorable. Think about it. We have a sum, not a difference. There's no common factor between the terms. We can write it as a squared quantity squared plus 2b squared quantity squared. But the sum of 2 squares doesn't factor over the real numbers. So where do we go from here? This is where Sophie Germain's insight comes in. And it's a technique that appears throughout mathematics. When you're stuck, try adding 0 in a clever way. Watch what happens when we add 4a squared b squared and then subtract 4a squared b squared. We haven't changed anything. We've just added 0. But now, let's rearrange the terms. The first 3 terms, a to the 4th plus 4a squared b squared plus 4b to the 4th. Can you see what this is? It's a perfect square. Specifically, it's a squared plus 2b squared, all squared. And the term we're subtracting, 4a squared b squared. That's also a perfect square, 2ab quantity squared. So our expression has become the difference of 2 squares. And here's the beautiful thing about the difference of 2 squares. It always factors. X squared minus y squared equals x plus y times x minus y. Applying this to our expression, we get a squared plus 2b squared plus 2ab times a squared plus 2b squared minus 2ab. And there it is, Sophie Germain's identity. A to the 4th plus 4b to the 4th equals the product of these 2 quadratic factors. Remarkable. But we're just getting started. The algebraic proof we just saw is elegant, but there's something even more beautiful hiding beneath the surface. A geometric proof that connects this identity to the Pythagorean theorem. Let's look at our 2 factors more carefully. The first factor is a squared plus 2ab plus 2b squared. Watch what happens when I rewrite this. I can group it as a plus b quantity squared plus b squared. Similarly, the second factor, a squared minus 2ab plus 2b squared, becomes a minus b squared plus b squared. Do you see what these are? Each factor is a sum of 2 squares. And whenever you see a sum of 2 squares, you should immediately think of the Pythagorean theorem. If you have a right triangle with legs of length p and q, then the hypotenuse squared equals p squared plus q squared. The sum of 2 squares is literally a hypotenuse squared. Let's build our first right triangle. The horizontal leg has length a plus b. The vertical leg has length b. By the Pythagorean theorem, the hypotenuse squared equals a plus b squared, which is exactly our first factor. Now let's build a second right triangle. This time, the horizontal leg has length a minus b. The vertical leg is still b. The hypotenuse squared equals a minus b squared plus b squared, our second factor. Here comes the magic. When we multiply these two hypotenuse squares together, we're multiplying our two factors. And we've already shown algebraically that this product equals a to the fourth plus 4b to the fourth. The geometry confirms the algebra. But there's something even deeper here. This geometric proof reveals a hidden connection to another ancient identity, the Diophantus sum of squares identity, which says that the product of two sums of squares is itself a sum of squares. Let me show you the numerical example with a equals 3 and b equals 2. The first triangle has legs 5 and 2, giving hypotenuse squared of 29. The second triangle has legs 1 and 2, giving hypotenuse squared of 5. Multiply 29 times 5, and you get 145. Now check, 3 to the fourth is 81, and 4 times 2 to the fourth is 64. Add them. 81 plus 64 equals 145. The geometry works perfectly. Now let me show you a third proof, one that uses complex numbers. This approach reveals why the identity works at an even deeper level. Remember that over the complex numbers, we can factor the sum of two squares. X squared plus y squared equals x plus iy times x minus iy, where I is the square root of -1. So let's factor a to the fourth plus 4b to the fourth using complex numbers. We can write this as a squared quantity squared plus 2b squared quantity squared. Factoring as a sum of squares gives us a squared plus 2ib squared times a squared minus 2ib squared. Through careful manipulation, we can factor these further. When we multiply conjugate pairs together, the imaginary parts cancel. And we're left with real factors, a squared plus 2ab plus 2b squared, and a squared minus 2ab plus 2b squared. Exactly Sophie Germain's identity, the complex numbers reveal the hidden structure. Now, let's see why this identity matters beyond pure algebra. Sophie Germain discovered it while working on Fermat's last theorem, one of the most famous problems in mathematics. Here's a stunning result. The expression n to the fourth plus 4 to the n power is never prime when n is greater than 1. Never. Not for n equals 2, not for n equals 1,000,000, not for any value. And Sophie Germain's identity proves it. Let me show you how. If n is even, then n to the fourth is even, and 4 to the n is also even. Their sum is even and greater than 2, so it's composite. That handles all even n. If n is odd, let n equal 2k plus 1. Then 4 to the n equals 4 to the 2k plus 1, which is 4 times 4 to the 2k. And 4 to the 2k is 2 to the k, quantity to the fourth. So n to the fourth plus 4 to the n equals n to the fourth plus 4 times 2 to the k, quantity to the fourth. This is exactly the form a to the fourth plus 4b to the fourth. Sophie Germain's identity applies directly. The expression factors into two terms. And when n is greater than 1, both factors are greater than 1. So the expression is composite. We've proven that n to the fourth plus 4 to the n is never prime for n greater than 1. This result appeared in the International Mathematical Olympiad in 1969. Problem 1 asked contestants to prove that there are infinitely many natural numbers, a, such that n to the fourth plus a is not prime for any positive integer n. The answer uses Sophie Germain's identity. A equals 4 to the k works for any k. Let me show you another application. Can you factor the number 104,060,465? It seems impossible without a computer, but watch this. Notice that 104,060,401 equals 101 to the fourth. Our original number is 101 to the fourth plus 64, which is 101 to the fourth plus 4 times 2 to the fourth. Sophie Germain's identity tells us this factors. Working it out, we get 1,613 times 9805, 6613 is prime. Sophie Germain's identity connects to a beautiful ancient result called the Brahmagupta-Fibonacci identity. The product of two sums of squares is itself a sum of squares. This identity was known to Diophantus, Brahmagupta, and Fibonacci. Remember our triangles? Each factor in Sophie Germain's identity is a sum of two squares, a hypotenuse squared. When we multiply them, we get another sum of squares. Sophie Germain's identity is one example of Oreffian factorizations. It also connects to cyclotomic polynomials and the multiplicative property of complex number norms. Interestingly, while the identity is attributed to Sophie Germain, it doesn't actually appear in her published works. The attribution came from Leonard Eugene Dixon's History of the Theory of Numbers in 1919. The history of mathematical attribution is often more complicated than it seems. Sophie Germain went on to make fundamental contributions to number theory and the theory of elasticity. She proved a special case of Fermat's last theorem that was the most significant progress on the problem for decades. She won a prize from the French Academy of Sciences for her work on vibrating elastic surfaces. Today there are Sophie Germain primes P where 2p plus 1 is also prime. There's a Sophie Germain crater on Venus. And of course, there's this identity. Gauss recommended her for an honorary doctorate, but she died of breast cancer before it could be awarded. On her death certificate, her occupation was listed as rentier, a person of independent means, not mathematician. The world was not ready to acknowledge what she truly was. So there you have it, Sophie Germain's identity in all its glory. We've seen 3 different proofs: the algebraic approach using completing the square, the geometric proof using the Pythagorean theorem, and the complex number factorization that reveals the deep structure. We've seen how this simple-looking identity proves that certain numbers are never prime, helps factor seemingly random large numbers, and connects to ideas ranging from ancient Greek geometry to modern abstract algebra. And we've learned about a remarkable mathematician who refused to let society's prejudices stop her from pursuing truth and beauty in mathematics. Sophie Germain wrapped herself in quilts and studied by candlelight because she knew that mathematics was worth any sacrifice. To every girl and every woman watching this video, if Sophie Germain could teach herself mathematics by candlelight in a freezing room, while the world told her she had no right to learn, then no obstacle can stop you. Your curiosity is valid, your dreams are valid. Whatever field calls to you, mathematics, science, art, anything, go for it. The world needs your mind. If this video helped you see mathematics a little differently, please subscribe and hit the bell icon. Leave a comment telling me which proof you found most beautiful. And until next time, keep looking for the geometry hiding inside the algebra.